Hello, my name is Marco Podda from the Department of Computer Science, University of Pisa, and I'm here to present the work of me and my colleagues titled Explainable Artificial Intelligence for Graph Data. Graph data, that is, data composed by nodes connected by relational edges, are ubiquitous. For example, molecules and social or traffic networks can be represented as graphs. To learn from this data, we can use deep graph networks, or DGNs, which are neural networks able to process the relational structure directly and learn tasks such as classification or regression from sets of graphs. To explain these models, we use explainable artificial intelligence, or XI techniques, tailored on graphs, most of which assign important scores to nodes. The more one node is deemed important, the more its influence is on the predictions made by a model. This is crucial to understand the predictions of DGNs, especially when they are applied in safety-critical tasks. Our work is based on using XI techniques to backtrack the inductive bias exploited by different DGN architectures. As you might know, inductive biases are a set of assumptions that make generalization on novel samples possible. Thus, knowing which inductive bias is at play could help selecting the right architecture for a task, facilitating the communication of results to decision makers. We started by noticing that common benchmarks can be solved by a DGN using different inductive biases. For example, the label of this graph can be learned by checking whether a grid motif is present, as you can see on the left, or by checking the node degree, and specifically whether there is at least one node with more than 3 neighbors, as you can see on the right. We use this fact to test different DGN architectures and XI methods to see what inductive bias they were using. Our first result is that we can indeed differentiate between DGNs. Some are better at learning by leveraging the degree pattern, and some others are better at learning by leveraging motifs. This seems to depend on the network architecture, and more specifically on the number of network layers. Indeed, for some architectures, we can start with a single network layer, and the network would pick up the degree pattern, as you can see on the left. But as we start increasing the number of layers, we see that the model gradually transitions from the degree pattern to the motif pattern. You can see this behavior in the rightmost plot. Lastly, we draw connections from our findings to topics in the graph theory literature. In particular, learning the degree pattern is similar to computing the cast centrality score for each node in the graph, while learning the motif pattern is connected to computing the Fiedler eigenvectors, which are related to the graph connectivity. Here is the bibliography of the works we produced. I hope I caught your interest, and if you have any questions, you can contact me. Thank you for your attention.